All right, section 24.6, this will be part one. There'll be several parts here. The first reaction we're going to cover here is a selective reduction of NO2 groups that yields an amine. Now, the best way to illustrate this actually is with a specific example. If we take an aryl nitro compound, say with an otherwise reducible functionality like an aldehyde, could be an aldehyde, could be an ester, could be a ketone, any of those that, for instance, we couldn't get selectivity with before. Now we know that the NO group can be reduced with palladium or platinum metals and hydrogen, but that will also reduce carbonyl functionalities. But if we use a low valent tin compound, this is tin dichloride, so that's a tin in the oxidation state too. This is typically done in a hydrochloric acid solution. The tin and the acid reduce the NO2 group. We then neutralize it with sodium hydroxide in the workup, and we produce a selective reduction. This only reduces the nitro group. And so this is a selective reduction of NO2. Now, the other, obviously, chapter 24 is about amines. So one way one could imagine making amines would be to alkylate nitrogen-containing compounds. So one could imagine taking NH3 plus methyl iodide, or any alkyl iodide, and you would react that and you would make methylamine. The problem is that this is more basic, as we saw in the last section, and that means it's more nucleophilic. So methylamine will react with methyl iodide again to make the dimethylamine, and this will just continue. Methyl iodide again to make trimethylamine, and guess what? It doesn't stop there. You can't control this with stoichiometry. It'll react with another methyl iodide. Now here it does stop, because we have fully alkylated the amine. And I've waited to put up the name here. So we can't, even with trying to use stoichiometric ratios to control things, get significant useful yields of these different kinds of amines, the primary amine, the secondary amine, the tertiary amine. But what you can see is that we can take it all to the end. So this is a method we call exhaustive alkylation or methylation. The most commonly used form of this is methylation, and we'll see that later in the Hoffman elimination reaction. So this is useful if you want to do basically the following reaction, taking any amine with an excess of the alkyl halide that you want. You can perform in what would be a useful process, exhaustive methylation. All right, so if we can't use sp3 nitrogen, that would be, electronically tetrahedral nitrogen, as the nucleophile, is there something else we can use? And it turns out there is. So in this part, I'll call this one C so that we have a clear distinction. This is what I'll call azide reduction. So if we have alkyl halides, and this is subject to all the standard SN2 limitations, because this is an SN2 reaction, we can take an alkyl halide plus azide. Okay, so this is azide. Typically we use it as a sodium azide solution. Azides can be explosive. You can easily see where one could imagine having nitrogen being lost there. So you have to be careful with these. There are things about numbers of carbons versus number of nitrogens that we understand pretty well in terms of how to make a stable azide. So this is a very good nucleophile. It's small, it's narrow, it does a simple SN2 reaction, and you get the azide. Then the azide can be very efficiently and easily reduced with lithium aluminum hydride to the amine. And this reaction works very well. Again, remembering we have to be able to do an SN2 reaction. So that means we are looking not at aryl but alkyl halides. So we could take the bromide, we react that with sodium azide. I'm going to put the charges there first, followed by lithium aluminum hydride. And you can make benzylamine that way.